Okay, we will start the presentation 8. Last week we saw that the electrode-electrolyte interface can be approximated, very grossly approximated. Please remember this, because this you should not think that it is the real picture. We will come to it. Even real picture is not possible. But anyway, first thing is metal electrolyte interface is considered as a capacitor. That is, when I polarize or apply a potential on the electrode, the oppositely charged ions in the electrolyte will organize themselves in a situation like this. The negative potential is on the electrode. The positive ions are organizing themselves in the electrolyte. This is equivalent to the capacitor. Okay, capacitor, one electrode is the negative electrode, another electrode is the positive electrode. How the potential will drop is shown here, that the potential will drop very steep linearly and then will remain constant within the electrolyte. So this is called the Helmholtz model of the double layer. If everything were to be very clearly like this, then it is very easy to mathematically track them. But unfortunately, this is not the truth. The capacitance, okay, of the double layer is given by epsilon r and epsilon 0 by the distance between the two plates. Okay, epsilon r is the relative permittivity, which is assumed not to vary with the distance, and epsilon r the permittivity of vacuum, and psi x denotes the closest approach distance of point charges. The decay of the electrostatic potential from psi m, okay, psi m to psi s, the solution phase potential, is linear, and Ch remains constant in the applied potential. So this is the consequence of this. This model has two very serious drawbacks. The interaction with ions in the subsequent layers to the first layer is neglected. It is as though that the ions are only in the first layer. That is what is assumed here. The dependence of the electrolytic concentration on the accumulation of the charges in the double layer has not been taken into account. We did not take into account the concentration changes that will take place because of this accumulation of the layer. So now this is called the Goy-Chapman model. Okay, we are only taking only 2 or 3 models which are very characteristic and very. So if I were to look at the electrode negatively polarized, the positive charges will be organizing themselves. Then the second layer and third layer, there will be some amount of organization, and finally the solution phase will take place. So therefore, when the first layer capacitance is greater than second layer capacitance, or when first layer capacitance is equal to second layer capacitance, the first layer alone is this. When the first layer the first layer capacitance and second layer capacitance are equal, then it is like this. So therefore the psi m is linear and then remains constant. This is the pictorial representation of ions in diffuse double layer. This is diffuse double layer of Goy-Chapman. So the capacitance is given by all these parameters. ER is the capacitance and the permittivity, and E0 is the permittivity in vacuum. Now, see this thing can be also approximated like this. A first layer is a compact first layer and a diffuse double layer. Okay, compact first layer where the charges are at a distance from the electrode, and then diffuse double layer. So therefore the psi m will now be will not reach the psi s value at the first layer, but it is a diffuse double layer. So up to this point is the diffuse double layer. So therefore we can say the capacitance will be the Helmholtz double layer capacitance plus the Guy-Chapman. This is a model of both of them together. That is, I hope you understand this. This is the this is the Helmholtz layer, where the first layer ions are compact layer. Here the diffuse ions are there, present there. Therefore, the first layer is a diffuse layer, first layer is a compact layer, and the diffuse layer. So therefore, the diffuse the psi m, the potential, electrostatic potential of the metal will vary like this up to the distance of the diffuse double layer. So this is the equation. So in all these models, we have left out the solvation of the ions. Okay, that is the first problem. So the ions, whether it is compact layer or not, the ions will be automatically solvated by the solvent molecules. Let us assume the water molecules. Water is a solvent. So therefore, the compact double layer as well as the diffuse double layer will be solvated. Now we have shown solvation as a fixed number. This may not be the fixed number. For example, here you can see this is three solvent molecules are close together and fourth molecule is little distance away. So anyway, we will not worry about it. The average coordination number of the solvent molecules may not be a constant thing. So therefore, this is the model proposed by Bockris. The arrangement of ions and solvent molecules represents a solvent molecule here represents the water molecule. The variation of the electrostatic potential psi as a function of the distance chi from the electrode is shown here. So therefore, the gradient change is called the inner Helmholtz layer. This is the outer Helmholtz layer. This is compact layer. This is the diffuse double layer. Okay, so therefore this is also is not a correct situation, because the average coordination number of the solvent molecules are not constant, and it can be on the electrode surface. The solvent molecules will be absorbed and also solvate the ions that are compact double layer. So therefore the model which we have to real model is a difficult situation to predict. All these models are only for metal solution interface. We have not yet gone to any other thing. In the metal solution interface, how the ions are arranged in the solution phase. So the first model for the structure of the double layer is analogous to a parallel plate condenser with a plane of charges on the metal and the second plane of opposite charges in the solution. According to this model, the capacity of the double layer should be independent of the potential across the metal solution interface, which contradicts the experimentally observed behavior. It should be constant with respect to potential, but it is not so. The next model considered that the changes in the solution side are not located in one plane, but diffuse into the bulk of the solution. This model yields parabolic dependence of capacity on charge. Though this model is satisfactory for very dilute solutions, very concentrations of the order of 10 to the minus 3 moles per liter, the predicted values of the capacity are far too high in concentrated solutions. So in concentrated solutions, the predicted value of the capacitance is high compared to the experimental value. So this model also is deficient. A combination of the compact and diffuse double layer model proved to be satisfactory. This is what we said. This is the model. Okay. However, in the very dilute solutions, it became in practice identical with the Helmholtz model, and in region of constant capacity, the dependence of the capacity on the radius of the ion present in solution is not seen, though the model shows this, and it cannot also explain the increase in the capacity which occurs in the anodic region. Okay, so these are all the drawbacks of these models. The three-layer model, the metal surface, the inner Helmholtz layer, that is the locus of the centers of the specifically adsorbed ions, and another outer Helmholtz plane, that is the locus of the center of the first layer of the hydrated ions, has several satisfactory features. However, it does not provide satisfactory explanation for the constant capacity observed in the negative branch of or the hump of the anodic side. So therefore, all these models are only approximate. They cannot be quantitatively giving rise to the behavior of the electrode-electrolyte interface. In all these models, the role of water or solvent was ignored, even though it is predominant species in the solution. Even if you take 10 to the minus 3 molar, the predominant species in the solution is the solvent molecules. The current accepted model is that the electrode is covered with a layer completely oriented water or solvent molecules, polarized. Okay. Specific adsorption of ions occurs in certain regions of the potential by replacement of some of the water molecules by partially dissolvated ions. Okay, we will see this. For example, you can see the solvent molecules are shown like this, and then it replaces the ions, and the solvent molecule replaces the solvent molecules. But still, in all these models, the role of water or solvent was ignored, even though it is the predominant species in the solution. So the second layer of water molecules is not oriented because these water molecules are under the influence of both the electric field and thermal fluctuations. They are like the secondary hydration sheath of the second around an ion. The second hydration sphere is not considered. Some of the water molecules can belong to the hydration sheets of the layer of the ions that are present in the outer Helmholtz plane. The dielectric constant, we are assuming a constant dielectric constant throughout the solution, but it is not true. The dielectric constant of the first layer of the oriented water molecules can be value between 6 to 7. Okay, let us assume less than 10. The second partly oriented water molecule layer can be 30 to 40. Okay. Whereas in the pure water it will be much higher. Considering the double layer as two capacitors in series, one with a low value of epsilon 6 and the other value of epsilon higher 40, the region of constant capacity with the potential may be understood. So now we will look at the electrode-electrolyte interface, how the potential will vary. So now you see the potential in the electrode is steeply coming down. This is called the surface potential. So chi m is the galvanic potential. We will come to it a little later. The steeply falling potential is the surface potential, and the slowly falling thing is called the volta potential. Potential variation as a function of distance from the metal electrode that is separated electrolyte solution without charge modification. Psi is the potential caused by the charge distributions when the electrode and solution are in contact. Okay, the psi. Okay, we are showing that. This is with respect to X. Now, from here we are going to go and look at other electrodes. Now we are showing a semiconductor electrolyte interface. This is what is more important. So now, in the semiconductor electrolyte interface, you can see that the semiconductor here is shown when it is positively polarized. The positive charges are also diffused there, not in the skin depth, but up to the bulk of the semiconductor. In the same way, negative ions, the first layer and second layer, and all, we are omitting here also the solvation of the ions. So this is the accepted picture, not the actual picture. Accepted picture of the semiconductor electrolyte interface. In the semiconductor electrolyte interface, up to now, I hope you are understanding this. Up to now, we have always thought that the potential will be psi m will be varying with respect to distance in the solution side, but it is not so. It is not so. The potential is varying in the solution side as well as on the semiconductor side or the electrode side. Okay, solid electrode side. So therefore, here I have shown it the potential, how the potential vary within the semiconductor, how the potential will vary. So dependence of the inner potential on the distance from the surface of the semiconductor X. Okay, this is the So how the semiconductor is within the semiconductor also the potential is varying. So now under these circumstances, these are all ideal pictures. Please remember this. These are all not real pictures. These are ideal pictures. So now what we are talking about it, you please concentrate on the middle of this diagram. The left hand side 3.5, 4.5, 5.5, 6.5 is the absolute value of the potential. Okay, so the zero of free electron in vacuum is assumed to have zero potential. That is the vacuum potential. Now, but what we are doing is we are not doing the potential. We are doing a potential with respect to an electrode. So therefore, the electrode here is a hydrogen electrode. So the potential has to be incorporated in terms of the potential of the with respect to the electrode. So therefore, on the right hand side, we are showing the electrochemical scale. This is the absolute scale, absolute potential scale. This is the electrochemical scale. So now approximately, it is not true, but approximately zero potential in the electrochemical scale corresponds to minus 4.5 electron volt in the absolute scale. So now let us assume that we are able to convert the absolute scale into electrochemical scale or electrochemical scale into the absolute scale. And we have already discussed that the potential, and the fourth quadrant is the positive value and the first quadrant is negative potentials. So now that is what is happening. So now let us look at the left hand side figure and then we will come to the right hand side figure. So we have an n-type semiconductor, a redox system. So therefore, when an electron from the semiconductor transfers to the, let us assume this is the curve that we are showing is the Fermi level is shown here. Okay, the Fermi level is shown here. Let us assume that I have so many species in solution which will undergo reduction. So the electron will go from the semiconductor to the solution side ions. So therefore the reduction will take place. In the same way, if the electrons were to be coming from the solution side to the electrode, then there will be oxidation will take place. So this is the picture which this is the metal semiconductor redox system, metal semiconductor electrolyte system. Instead of that, we have p-type semiconductor and the redox system. The picture will be slightly different. That's all. Otherwise, all of them. So we will assume that this is the density of states of the density of states of receiving electrons or the density of states of giving the electrons. The same way here also. We will assume that. Okay, it is not true, but we will assume the density of states in the solution side. So at a certain potential, the Fermi level lies at the same energy as the solution redox potential. So if I were to apply a potential, then the potential here will be equal to the potential at the electrolyte side and the electrode side. The potential will be the same. There is no net transfer of charge. When the potentials are same, I hope you are able to see. If the potentials are same, then no charge transfer. If the potential is higher, then the charge transfer will take place because the electron will be more stable on the electrolyte side in the n-type semiconductor. There is no net transfer of charge when the potentials are equal from the solution side as well as the semiconductor side. Hence, there is no band bending, and this potential is therefore referred to as a flat band potential. Okay, we will assume this. We will have occasions to discuss with the flat band potential very carefully little later. Depletion region arises at the potentials positive of the flat band potential for an n-type semiconductor and at potentials negative of the flat band potential for a p-type semiconductor. This is a statement. At potentials negative of the flat band potential for n-type semiconductor, negative. The potentials are negative means here you see. So therefore, the potential here is the electron potential. So therefore, this is the potential receiving species in the electrolyte. Therefore, the charge will be reduction reaction. At potentials negative of the flat band potential for n-type semiconductor, there is now an excess of majority charge carriers, electrons in this space charge region, which is referred to as accumulation layer. An accumulation region arises in a p-type semiconductor at potentials more positive than the flat band potential. I hope you are able to see that. If the potential is more than the more positive with respect to the equalization potential, then the depletion layer will be there. So we will take this up later. We will for a certain value of the applied potential, there is equality between the number of electrons removed from and supplied to the electrode. In this situation, there will be no space charge region, and the potential is called flat band potential. If the charges were to be transferred here, then this potential will become equal to the Fermi level. So therefore, that is the flat band potential. When the potential is not is flat, electrons accumulate in the space charge layer by injection, giving rise to an accumulation layer. Electrons are removed from the space charge layer, creating a depletion layer. The force necessary to extract electrons from the electrode is so great that they are extracted not only from the conduction band but also from the valence band, equivalent to hole injection. Okay, electrons are, I hope you are able to see this. Electrons are injected from here, holes are injected from here. The force necessary to extract electrons from the electrode is so great that they are extracted not only from the conduction band but also from the valence band. An inversion layer is formed because n-type semiconductor is converted into p-type semiconductor at the surface. Adsorbates means the ions in the solution, okay, can facilitate this process. So now we are showing you what are the species that can undergo reduction and oxidation, or electron transfer from the electrode to the semiconductor to the solution side, or from the solution side to the semiconductor. Let us take only one or two examples. Enough, that is enough. Here we have placed all the important semiconductors. What we are thinking of is, we have already seen that if I want to do a good semiconductor, photoactive semiconductor, for example, strontium titanate, then the conduction band is more negative with respect to the hydrogen evolution potential. The dotted line is the hydrogen evolution potential. The valence band top is more positive with respect to the oxygen evolution potential. So therefore, SRTaO2 can promote the hydrogen evolution reaction and oxygen evolution reaction in water decomposition. Now here we have shown various silver. We are not talking about the water decomposition. We are talking about the reduction of or oxidation of various species. For example, take for example silver plus, or chlorine gas and chloride, or bromine gas, bromine liquid, or bromide, like that. Okay, the titanium 2 plus, titanium 3 plus, these type of redox reactions. Aluminum to aluminum 3 plus, manganese to manganese 2 plus, zinc to zinc 2 plus, fluorine to fluorine F minus, all those things. So here we are also showing some typical values of the polyanions or polycations. So now what it means is relative energy levels of some common semiconductor electrode materials and the redox potentials. So in this picture, we have not put all the semiconductors, but we have put representative semiconductors. I hope you are able to see what is representative here is The conduction band is more negative with respect to hydrogen evolution potential. The valence band is more positive with respect to oxygen evolution potential. There are few semiconductors which are shown, which are, for example, silicon. Silicon you take, the conduction band edge is more negative with respect to hydrogen evolution potential. The valence band potential is not more positive with respect to oxygen evolution. So silicon cannot promote the oxygen evolution reaction, only hydrogen evolution reaction. That is why silicon is, even though a semiconductor, is not considered for water decomposition reaction, because it cannot decompose. Even titanium dioxide also is the same case, pure titanium dioxide. It cannot evolve hydrogen, but it can evolve oxygen. Okay, that is why we are always looking at modifying titanium dioxide so that the conduction band edge will be more negative with respect to hydrogen evolution potential. So now, what is the situation? Is the question. So now we have to look at a few important parameters. Now you look at this. Now the oxygen evolution reaction potential is given here with respect to 0. We have already seen 0 is 4.5. With respect to it, 1.23 volts below that. Now, if the electrode itself is capable of undergoing some oxidation reaction, for example, zinc oxide, if you take zinc oxide plus 2 H plus 2 electron gives rise to zinc. So zinc 2 plus gets oxidized to reduced to zinc. So okay, this is the hydrogen evolution reaction. Zinc oxide is getting reduced, is getting dissolved to give rise to the zinc ions. So therefore, if this potential of this redox reaction is more positive, less positive with respect to the oxygen evolution potential, that will be the preferable reaction, because the free energy change of this will be more negative compared to the oxygen evolution reaction. The same thing is also good for the hydrogen evolution reaction also. So if the hydrogen evolution reaction potential is less negative with respect to a decomposition reaction, then the decomposition reaction will be favored. So therefore, relative positions of redox potential of substrate and semiconductor dissolution for zinc oxide at pH 0. So therefore, we have to be very careful in choosing the semiconductor. It is not enough. I have to look at the conduction band edge is more negative with respect to hydrogen evolution potential. The valence band top must be more positive with respect to oxygen evolution potential. But also we should see whether the constituent ions can undergo reduction or oxidation. Then that reaction will be predominant. This is what is called the photocorrosion. So now we will take it up later on, all other things with respect to, because we have to talk about electrophoresis, electroosmosis, many other electrochemical processes that will take place, electrode electrolyte interface. But okay, so the 4 manifestations of, we will only take only 2 of them: electroosmosis, electrophoresis. Electrophoresis is charged solid particles, colloidal particles, moving through the liquid under the influence of an electric field. It is called the sedimentation potential when it is due to gravitation force. If the ions are going to sediment, then it is gravitation force. If the charged particles are moving around under the influence of electrical field, then it is electrophoresis. Electroosmosis is liquids moving past a charged solid surface, possibly through a membrane, under the influence of an electric field. This is called the streaming potential when it is due to an applied pressure difference. We can pass the solvent, okay, reverse osmosis. The water is going through the membrane. So therefore, by applying a pressure, we can take a solvated water or salted water and prepare pure water from this impure water. These effects are normally studied in fine capillaries in order to maximize the ratio of the solid surface area to the liquid volume. We will take it up the next time. what is this? Only we will see the four combinations: solid, liquid, electrophoresis, electric field, electrophoretic mobility via mass transport of the measurement, solid liquid sedimentation potential, force of gravity, potential difference, liquid solid electroosmosis, electric field, rate of liquid movement, liquid solid steaming potential, pressure, potential difference. This is the thing. So this is the same thing is put here in a different manner. So we will look at them. The size of the particles that is calculated from these experiments corresponds to particle dimensions plus the double layer thickness. The shear plane is defined such that inside the absorbed species are rigidly held and outside it there is a free movement. Their shear plane can therefore be associated roughly with the outer Helmholtz plane. I hope you are remembering the outer Helmholtz plane. This is the IHP is inner Helmholtz plane, OHP is the outer Helmholtz plane. The value of the electrostatic potential at the shear plane with respect to the value of the bulk solution is called the electrokinetic or zeta potential, the potential difference. Okay. So this is a summary of what we have tried to do. The metal electrolyte interface ideal picture is shown here. So the 1 hour capacitance will be equal to 1 hour CH and 1 hour Guy-Chapman and Helmholtz plane. The density of states in the metal will be 10 to the 22 say, per cubic centimeter per volt. The charge, space charge of the metal is all squeezed onto the surface. That is why it is skin depth. Field gradient is absent in the bulk of the metal. Okay, we have already talked about it. Only in the semiconductor the field gradient is there. Electron transfer at metal electrode interface is governed by only the potential difference. If the potential difference is different, then the electron will be supplied from the metal to the electrolyte or from the electrolyte to the electrode. The corresponding equations are given here. Okay, we will take it up here. When we go to the semiconductor electrolyte interface, the capacitance of the double layer is not only the the Helmholtz plane, Guy-Chapman plane plus the semiconductor solution interface capacitance. This is called the Garrett-Baratin space charge inside the semiconductor. The potential due to atmosphere of hole and electrons is given by chi. Okay, this is a rough. Once again, it is very rough, very because the ideal picture or the real picture cannot be drawn. That is why we are looking now. The capacitance in the case of a semiconductor electrolyte interface will be adding one more term. So when I do this, the energy bands near the semiconductor are disturbed by the existence of the field. The bending of the bands up or down depends on the sign on the ionic charge populating on the outer Helmholtz plane. Field penetration exists inside the semiconductor, we have already told. Field gradients are dependent upon density of states, surface states. We will take it up the quantitative aspects of the electron transfer on the semiconductor to electrolyte interface next time. Now you can ask any questions you have, because this is a very important area for us. You can ask any questions you want.
Hello, sir. Sir, can I ask question from the last class?
Yes.
So I have a doubt in polarization, sir. Actually, what is polarization and how can you apply this polarization current and polarization? It is just like over potential or what? Polarization contributes to over potential, so I have just a confusion in that.
Okay. Assume that you are having a girlfriend.
No. Yes, sir.
Assume.
Yes, sir.
polarization. I'm explaining to you polarization. That is all.
Yeah,
Okay, don't
yeah,
worry
yes,
about the
yeah,
girlfriend.
yeah, yes, yes,
So now you are, when I look at you, assume
yes,
that I do not know that you have a girlfriend.
yes, sir.
So when I look at you, I will look at you as a human being.
Yes, sir.
The same human being, when your girlfriend is there, the behavior will be different.
Will be different. Yes.
So this is what is called a polarization. I
So
will
this is
explain to you now in a minute. I will tell you. So
yes,
now if I have an electrode,
yes, sir.
okay,
Yes, sir.
and I have not put any potential on the electrode, then I have not polarized the electrode.
It is in
When
open
I
circuit
have,
condition. It is in open
huh?
circuit condition. It is in
Yes,
open
yes,
circuit condition. Okay.
yeah, yes. Open circuit condition and closed circuit condition.
Okay.
Polarization is applying a potential.
Okay. Now understood. Sir, there are activation polarization and concentration polarization also.
Yes,
So,
yes,
so they also sir contribute to overpotential or not?
definitely, definitely. Polarization itself is can be considered as a part of our potential.
Okay. So how can you supply the polarization current? Means we have told somewhere that in absence of polarization current, it is reversible. Means irreversible potential
Hmm.
for water shooting in one plate. So how can you apply a polarizing current? How can any potential will apply to generate polarizing current, or we have to supply certain potential that is equal to the polarization value?
Yes. For example, when I take an electrode, it has to dissolve. It has to dissolve means only at a certain potential only it will dissolve.
Yes, sir.
Below
So
that potential, below is not correct. Less than that potential, the dissolution will not take place. But the electrode is polarized.
for example, I am taking zinc. So
Hmm.
zinc will dissolve at so minus 0.76 volt. So if I
Yes.
apply less than minus 0.76 volt, so I am not polarizing the electrode.
You are
That,
polarizing the electrode, but not carrying out an electrolysis.
okay. So if I supply any potential, then polarization started. Let
Yes,
it be
yes.
below that or above that.
Yes, yes. Below that, it will only polarize the electrode. No electrochemical reaction will take place.
It will just like act like a inert electrode or ideally polarized electrode like that.
Yes, yes.
Okay. So after I have exceed minus 0.76 volt, so I will supply that polarizing current. Now
Yes,
polarizing current will be generated.
yes.
Okay. Okay. That was my doubt. So that was my doubt about that polarizing current and what is that polarizing current and when it is present and when it is absent. So that was my doubt.
Okay. I hope it is clear now.
Yeah, it is clear now.
Any other questions? This is
Today's
IMMT, yeah?
yeah, I'm Nanda sir. Yeah.
I know, I know.
So I will have many questions in the next class over these models, Goy Chapman model and these models because I have to go
Okay,
through that now
okay, okay. But
because
this
it
is
was
very
bit too fast. It was too fast, so I could not catch up actually those things. Then I will again see the recording and
uh,
go through word by word. Then I will ask you question about this in next class.
definitely, definitely. You can ask. There, there, there are many other people there.
No, not one place. They are attending in their own lab.
Okay, okay,
Mm. I am attending in my place, on my sitting place.
okay, okay. Outside your boss room.
Yeah, not outside my washroom, on the other lab, the
Okay, okay,
second lab. I am sitting in the
okay,
second lab.
okay, okay.
Yes.
sir. Hello, sir.
Yes.
Hello.
Any questions?
So can you please show the slide of the semiconductor electrolyte interface? That slide.
Okay. Uh, I will show. I will show. Okay. These are all ideal pictures. We should not think that this is the truth. Okay. Tell me.
Okay. So it's one metal electrolyte. So
Your
when
mic is some right.
but
Why don't you
when coming
type?
to the hello sir, hello.
Tell me.
So when we are calculating, you said that we want to add one more factor semiconductor is diffuse layer plus one factor for the semiconductor,
Oh,
right?
okay, okay. That equation. I will show you that equation in a minute. Okay, this equation.
Yes, sir.
This equation.
Yes, sir. Can you please explain in understanding that means because it is entirely different
No, no. See, we have
sequential
already
orientation of the thing.
done when it is a metal solution interface. Then it can be the capacitance will be Helmholtz capacitance plus the diffuse double layer capacitance, Guy-Chapman model and the Helmholtz model. Whereas when we
Okay.
take a semiconductor electrolyte interface, this is also very gross. We must understand this is not the exact one. Okay, we are adding one more term for the potential drop. You can see the potential drop here. This is the potential drop in the solution phase. The potential also drops in the semiconductor. This is the semiconductor. This is the solution phase. I hope you are able to see. So therefore, the
Yes, sir.
potential is dropping in the within the semiconductor. Therefore, this will also have a capacitance. So therefore, that is what we call as the one additional term. If everything is ideal, the capacitance in the semiconductor, in the capacitance in the Helmholtz plane, in the outer Helmholtz plane and the inner Helmholtz plane, if all of them are constant value, then this equation is valid. This is one of the ways of understanding this. Now, my real system will be different from all these three because there will not be no ideal compact layer, there will be no ideal diffuse double layer, there will be no ideal potential drop within the semiconductor. So, in real systems, the situation will be very difficult, but
So why there is
it will consist of three terms.
okay, sir. Sir, why there is much potential drop for the semiconductor? Because what's the reason?
Because we are going to do that because you have not studied solid state chemistry or solid state physics. Anyway, if you take the metal, the potential will be the same on all the metal surface. Whereas when you take semiconductor, for example, zinc oxide, zinc 2 plus ion, O2 minus ion. Therefore, the potential is not same. The potential is not a periodic potential.
Okay, okay. Sir. Now I got some point. Okay. So, sir, if suppose we are taking an n-type semiconductor for any reaction, okay, say a reduction reaction. So, suppose we are taking a n-type semiconductor for a reduction reaction.
Okay.
Then, for certain semiconductor, the reaction is feasible. Means the reaction is happening or it is is higher, right? Means that